Hello folks, welcome to Rational Science. I'm going to do a little thing that most people are familiar with, you know. Got a little spoon here, wooden spoon. I'm going to let go of it. And if you do this at home, you'll find out that it always falls downwards, you know. Here it is. I've done it a million times and always falls downwards. And the funny thing about this is that we've known about gravity since we were monkeys. And it turns out not a single mathematician on planet Earth can tell you what causes, you know, the spoon to fall to the floor. And you say, oh, it's impossible, Bill. We'll never figure it out. It's just beyond human ability. And it turns out that, you know, this is the easiest thing in the world. It's baby stuff, kindergarten stuff. And people say, no, how can you say we haven't been able to figure it out because it's just impossible? They've gone off out there and tried to figure out things like, you know, holograms and black holes and dark matter, and they go through all these things, and all I want to know is why a spoon falls to the floor. And no one can tell you that. And again, people think this is impossible, that it's beyond our capability. And I think it's the simplest thing in the world. So here you have, you know, a spoon falling to the floor. And it turns out that you want to know how that happened, why it happened, what causes it to happen. And so what happens? Turns out that you come across, you know, a Aladdin's lamp, rub it, genie comes out, or maybe you find yourself a leprechaun, you know, and he grants you a wish. And he says, what would you like, master? I say, I want to know what causes gravity. I want to see, you know, with my own eyes, you know, what is causing that. Don't you prefer a beer or to sleep with a beautiful woman? No, I want to know the cause of gravity. I want to see that. Okay. And so he grants you that wish, and it turns out that you are able to see finally, you know, the invisible objects that are coming in contact with the spoon. You see something maybe like this, okay? You see all these pixels, these pixies, you know, pushing the spoon downward from above. Maybe they show you that. Maybe they show you something like that, you know, something like this, and they say, look, what's happening here is that you have every atom of the spoon is bound to every atom on Earth. And what you're doing essentially is, you know, having that thing, the spoon fall, and all these mediators just fanning out. And I'm not asking you to believe in one or the other. The issue is something else. The issue is, you know, all we need to do to figure out gravity is to figure out what is in contact with the spoon. If we can figure out what's in physical contact with the spoon, hey, we can, it's baby stuff, it's kid stuff. Just like you just saw there, I can illustrate it and everything. Whether it's push or pull, you know, I should be able to explain it. And it turns out that in the last 10,000 years, not a single mathematician even thought about that. Everybody thinks that, you know, nothing is in contact with the spoon because you can't see anything or touch anything above or below. So they conclude that that this just falls because whatever. And so they have never figured it out. And the question is, what is the problem? Why haven't we figured something as simple as this in the last 10,000 years? And it all comes down to the mathematical method that we've inherited from the 17th century. You know, you had the Greeks, and they were the ones who set the foundations of science. They set it on quicksand. You know, it was doesn't have solid foundations. And in the 17th century, instead of wiping out everything that the Greeks had done, they simply added experiments and predictions, you know, and so on, everything related to experiments. Says you got to test the hypothesis or whatever. And so this is the mathematical method that we have inherited and we still run even to this day. And what it consists of, you have an observation, you see something happening, you try to explain it. In fact, that's no longer part of the scientific method. Here you have Mr. Richard Feynman, Nobel Prize, I think 1965. There it is, 1965. And he said, theoretical physics has given up on explanations, on physical interpretation, on trying to explain, mechanism. He says, the more you see how strangely nature behaves, the harder it is to make even a simple model, right? That you can explain that even the simplest phenomena actually work, how something simple works. And so we don't do explanations anymore. A lot of the mathematicians today, they believe that's not part of what they do or what they should be doing. They think all they do is equations, measurements and equations, that's it. So what the mathematicians of the 17th century added were experiments, predictions, describing mathematically. Until then, they were doing some math, but it was primarily, a lot of intuition, logic, that kind of thing. And these people said, no, you got to be a little more scientific, meaning let's measure, let's verify what's happening, and come up with equations. So you had to do an experiment. And so this is what we have today. Essentially, a lot of people equate technology with science when it has nothing to do one with the other. Technology, something you develop, a gadget that you develop by trial and error, and science is something totally different. Science is explanation. I mean, what are you asking? You're asking, how does gravity work? Why does it work the way? What is the cause? That's what you're asking. None of these steps will answer that question. None of them. And so, what we should do is get rid of it. That's the solution to this problem. This is what's preventing us from understanding how the universe works. So what I've done is what they should have done, and that is erase the entire board completely and start all over. I mean, throw the baby with the wash water, the whole thing. So do we need to do that? Yeah, we need to absolutely get rid of all of it. None of it is science today because we don't have a rational explanation out there in physics. And that's where the problem is. Do we have the right people doing this? Are the mathematicians the right people to be doing explanations if they've already given up, according to Mr. Feynman? So they've given up on that, on explanation. If they've given up, then we're asking the wrong people. They were never qualified to begin with. All they do, according to them, is measure and get equations. And that's not going to give us an explanation of anything. So not only do we not have explanations, but we have the wrong people doing what we think they should be doing, which is getting explanations for us, some physical interpretations. So what I've done is I've erased the whole board completely, and we start all over because we don't even have the right definition of science. What is science? Okay, and so here it is. That's what science is: rational explanations. Okay, science is divided in two parts: physics, which is what we do here, and it's also involves philosophy. But philosophy, again, nobody has ever defined what philosophy is. So we define it now and say it's rational explanations of reasons and purposes, whereas physics is the rational explanations of causes and mechanisms. Okay? And no, people say, well, don't you do experiments? No, we don't have to do experiments. In fact, there are no experiments in science. You can do whatever experiment you want in your dark basement. No problem. Go ahead and do it. But when you come to the conference, we don't want you doing an experiment. Especially specifically, we don't want you doing an experiment because then now you're trying to convince us that your theory is correct. That's why you're doing an experiment. No, we don't do experiments in physics. We don't do experiments in science. What we do is we explain rationally. Okay, we explain whatever we concluded, from our experiments. So, like I like to say, we don't do experiments. We explain them. That's what we do in science. People think that science is about doing experiments. Absolutely not. And science is not about doing equations because equations can only describe. And in science, we don't describe, we explain. That's what we do in science. Okay, and so we got to get the goal of science and of physics right, and that is that it's got to do with rational explanations. And so what is a rational, and what is rational, what is explanation? I like to define irrationality, which is probably easier to comprehend or understand. Okay, here it is. These are the criteria for irrationality. Okay, and the main one is that first one up there. Treating concepts as objects, and reification, concretization, and then moving the object around, the concept around. You've already converted it into an object. Now you're saying, oh, I'm moving a field. Oh, I'm moving time. I'm warping time. No, you can't do that in physics. What you've done is you've taken a concept, you turned it into a physical object, and now in your presentation, you're presenting it, or you're treating it as a physical object. Totally irrational. Then obviously the important second one is there, that you have to define the key terms. And a lot of people, especially I've had lately a few etherists, and they don't want to define their terms. They say that it's word salads, just a bunch of noise that they hear, and they say, no, I came here to do physics. Well, physics is 150% word salad, definitions. You must have definitions, otherwise you cannot convey your thoughts. They thought they conveyed their thoughts, and again, they do the same thing as the establishment. That is, they treat concepts as physical objects. They thought they conveyed that property to the crowd, to the audience, when they did not. Okay? And then there's a couple more criteria there for rationality, but again, the first two are the main ones. And then what is an explanation? Well, a lot of people think that an explanation is a bunch of descriptions. No, it ain't. Okay, it ain't. Explanation gives you something descriptions usually don't. In fact, I don't think any description can really give you an explanation of the causes. Cannot tell you the causes. Okay, and that's the main reason, the main difference between explanations and descriptions. Describe a mathematical equation can describe. It cannot tell you what caused something. It cannot tell you what exists. For that, math is no good, or a description is no good. Before you can describe something, hopefully you put it on the board or on your screen or wherever. And then you can describe it, yeah. And so, if you look up the scientific method we have today, the one that we're proposing is in line with this definition of science, which is rational explanations. And this is as it pertains to physics. We need to present the objects that are going to play an important role in our theory, right? You got to show the object. You're going to give a physical interpretation. So hopefully you have something physical on the board, meaning an object, a thing. Okay? So that's the first thing that you got to present to the audience. They need to see what objects you're going to be doing your theory with. Then you have to have the definitions, and you got to present like the initial scene. Like before you put, a theory is a movie, and all movies start, at the beginning, at the first frame. They don't start in the middle of the frame of the film, and this is where a lot of people start. They want to skip these steps, and they say, "Let me tell you my theory." No, don't tell me your theory. I want to see the objects first. I want to hear your definitions, and if you don't have them, we're going to withdraw the microphone from your mouth. You are not allowed to talk yet. Okay, you're not prepared to talk. Okay, so what I've done is created the foundations of physics. Okay, that's what I call it. Here you have what is known as the foundations of physics. What are those? Well, we need to define words. That's where we start. You can't begin your theory or science in general unless you start with definitions. You need to tell the crowd what your definitions are, and they don't have to be from the dictionary. In fact, I strongly recommend you never use a dictionary, because there's not a single one that I've found that has a rational definition of words that we use in physics. They have always been defined either by so-called philosophers or English majors or language majors and so on. Not one of these definitions that we'll see right now are rational, coming out of any dictionary or encyclopedia on planet Earth. Okay, so here we have what I call the golden principle of physics. You cannot do physics without a physical object. You need an object. Okay, if you don't have an object, what kind of physics are you going to be doing? What are we going to be seeing? What mechanism are we going to be seeing? I mean, we're looking for causes, right? For causes, you need to have a physical object that does something, pushes, pulls, interacts somehow with another object, and you see all that happening on the screen, or you hear it, someone explains it to you, and now you understand the theory. Okay? Doesn't mean you agree with the theory, it just means that you're going to understand what the presenter is trying to get across. Okay, that's the point here. So if physics requires an object, I'll let you guess. What do you think is the first word you need to define in physics? Well, you need to define what an object is. And it turns out no one in the last 10,000 years, ever defined what an object is. And so we have to do it now. Okay, and here it is. This is what an object is. It's that which has shape. And you say, just a simple definition, nobody ever discovered it? Yeah, because everybody was concentrating on the wrong properties, attributes of objects. They said, well, an object's what I can see and touch. Absolutely not. Those two are irrational criteria. The only rational criteria is shape. And please don't say, well, what do you mean by shape? Yeah, we have all these people who come up with as devil's advocate, extreme devil's advocate, and they say, oh, what do you mean by that? And what do you mean by which? And what do you mean by has? No, we don't do that inside. We don't define every word in the dictionary. All we need to define is the word object. And we're saying is that which has shape. You want to know what shape is? Go to a kindergarten tomorrow and take a ball that's of the same material as a cube, and you show them to the kids, and you say, what is the difference between these two? They have the same volume, same everything. What is the difference? And the kid will say, it's a shape. That's what they'll tell you. They'll teach you what shape is. Okay, so we don't need a definition for shape. We all know what shape is, and the common notion of shape is just fine. But what is the problem? The problem is this, that we've had all these definitions throughout history, and most of them from so-called philosophy that has no business defining the word object, because the word object belongs exclusively to physics. It does not belong in philosophy, ontology, metaphysics, or any of that nonsense the Greeks invented. No, the word object belongs exclusively to physics. It's a physicist who's got to define the word object. And if you never put it in if you're a theorist or you're doing research or whatever, and you got to, you're trying to explain your theory, you're writing a book or whatever, if you've never pondered the word object, if you never really pondered, what is an object, then you are not really meant to be a physicist, okay? Because that's a word that should have popped in your eyes. And you can go through any textbook of physics on planet Earth, okay, so-called physics, mathematical physics, whatever they teach in high school, college, you will not find in any textbook that so-called physics that it begins by defining the word object. And it's the first word we had to define if we're going to give a physical interpretation. Obviously, if it's not in any textbook on Earth, no one in mathematical physics believes that physical interpretations are part of physics. You get any of these books and they go directly into math. They say, well, what is the mass of the Earth? And this is how we calculated it, and so on. That's not science. It's got nothing to do with science. Science we explain. We don't describe. We don't say, what is the mass of the Earth? What is the mass of the sun? We don't care about that nonsense. Okay? We want to know why the Earth goes around the sun. What causes that? Why doesn't the Earth fly away? That's what we want to understand. That's physics. But saying that, the mass of the Earth is such and such, all you're doing is making a relation and giving you a calculation. What have you explained with that? Okay, so you see all these definitions of thing or a concept. No, an object is not a concept. Concept is a totally different word. It's nothing to do with object, with thing. A concept is not a thing. Okay, these are two different words, especially for the purposes of physics. You cannot confuse a concept with an object. Object, an abstract one they have, these are different definitions I pulled out of different places, does not exist at any particular time or place. No, you can't talk about exist yet. We haven't gotten to the word exist. We'll get to that 2 years later. Right now we're still figuring out what an object is. The word object has really nothing to do with the word exist. In other words, you can't use the word exist to define the word object. That's what they've done here in the abstract mode, abstract object. The physical one, a collection of matter. Absolutely not. Collection of matter is a concept. Matter is a concept. Okay? Why is matter a concept? We'll find out in a minute. But matter is not a physical object. So you cannot say that an object is a collection of matter. Matter just means many objects. That's all it means. And so many objects is not a thing. It's a concept. And we'll find out why. In grammar, any word that is a noun that you can put in as a subject of a sentence is an object. Not in physics. Okay? We cannot just use the word motion, which is a noun in ordinary speech, and put it in the sentence and say, oh, the motion of the turtle. You know, you can't do that. Motion is not a physical object. It's a subject, yeah, for grammar, but it's not an object for the purposes of physics. Okay? Again, motion is a concept, dynamic one, in fact. Then you have that last one, the famous one, which is the visibility and tangibility criteria. Absolutely not. You need visible or tangible requires a second object. So you're already invoking a second object, whether you know it or not. And you can't use the word anything, because anything is the word we're trying to define. Anything and object are synonyms. So you cannot say something or anything or a thing, because those are the words we're trying to define. So you can't use a synonym to define a word. Never. And so, yeah, the two criteria are wrong, and you can't use a synonym to define. And then it talks about can be perceived by the senses. No, we don't perception anything. We don't perceive. Okay, it's perceive requires another object known as a human being or whatever. I mean, you don't even need to be perceiving. You can say that sight and touch require two objects. You know, because the asteroid is not an object until it hits the moon, until it touches. Maybe you didn't see it because it doesn't have eyes, but it hit the moon and touches. So now both the moon and the asteroid become objects. They were not objects until they hit each other, they touch each other. So again, all these are irrational definitions. We can't use them in physics. The only one we can use is that which has shape. Shape is a universal property of all objects. Okay? And here we have some of the properties of this word. It's just so, because people have a lot of questions, I can only summarize them here. I'm not going to spend all day on the word object, but an object in physics that you present is made of a single piece. And it takes a long time for people to understand that. When you point and say table, you're not thinking, oh, but it's made out of atoms, and every atom has all these electrons rolling around it. And no. The word table, you point, it refers to that thing that you have in front of it as if it were a single piece. Okay? Elephant, made of a single piece. Tree, made of a single piece. Rock, made of a single piece. We never ask what it's made out of. That's why that which is made out of matter, absolutely irrational definition. No object moves within a photograph. Some people are telling me, well, within the photograph you still have the electrons which are spinning around in for every atom. My God, these poor people. What are they doing in physics? No. This is very simple. I used the Universal movie. I didn't bring an example of that today, but I should have maybe. But the Universal movie, you know, God's Universal movie, or Father Universe's Universal movie, in every single frame, everything is standing still. Even every electron, every photon, everything is just standing still in a single frame. If you want to see an electron move, right, you need to have at least two frames in the Universal movie. But for a given frame in the Universal movie, a cross-section of motion, all you have are static concepts such as distance, location, existence. Okay, and that's all you have. And so, you know, people have trouble because they have all this jumble motion in their heads. They say, oh, but water moves, and air moves, and the ether moves, and my God, no. Nothing moves in a single frame of the Universal movie. Nothing moves. Everything is just standing still at a given distance from everything else, even the electrons. Okay, they don't move around the atoms. You want to see an electron move, you need to have a second frame of the film, a third one, fourth one, fifth one, and then, yeah, you can see the whole strip and find the electron moving, if that's what you think an electron does. But for a single frame, No motion for anything. And they don't understand this. They get, all confused with this notion of motion. Okay, when you present an object, it's the only object in the universe. There's no other object. Okay, so I like to say that all objects are standalone. In other words, I have three examples that I usually present. One is the halo. The angel has a halo. Without the halo, without the angel, all you have is a ring. So you don't call it a halo. In order to have a halo, use the word halo, you need to put the Spirit, the Holy Spirit in there. Okay? Then it becomes a halo. Otherwise, without the angel, it's just a ring. And so every object stands alone. A halo is not an object because it requires another object. Same with a shadow. Shadow, you can't do it without the tree. Okay? You need the tree, you need the sun or some light. And so the way we show that a shadow is not a physical object is that you take the tree out into space. The tree is still there, but the shadow is gone. No more shadow. Okay? If it bothers you, besides, the shadow goes all the way to the root of the tree, so it's not an independent object, standalone object. And a region, the same thing. Other people have a problem with that because they confuse, like in a field, they say, well, this is a region here where something is happening. Yeah, but a region is not a physical object. Okay, so there's something happening in there. You have to identify the objects that are moving in there. But you can't say, oh, this whole thing, the field, magnetic field, the electric field, the gravitational field. No, field is not a physical object. Okay, field is something that has something in motion in it, usually like in the case of magnetic field. And what you have to identify is those lines of force that comprise the field. You got to identify what those are. And they've never done that. They just call it the field. Look at the whole shebang, and they just use the whole word. Oh, the field is moving, the field is vibrating, and so on. And we don't use adjectives to qualify objects. There's no such thing as a dead cat or a black cat in science, in physics. Okay, no such monster. There's a thing called a cat. Whether it's black or big or small or large or dead or alive. That's not part of the word cat. Only a cat is an object. Okay, we don't qualify anything with an adjective or an adverb in front of it. Okay, so, and we'll see some examples later on probably. Okay, but let's move on here. We absolutely need to define what space is. Okay, so that's the second word, because if an object is that which has shape, space is that which doesn't. One is something, the other one is nothing. Synonym of nothing. Yeah, right? And here you have it. Little rundown. Shape is the only universal property of objects, right? And there's no object that doesn't have shape. Something and nothing are antonyms. So now we can use these two definitions consistently in our presentation. It's a comprehensive system of definitions. One is related to the other in the sense that in this case they're antonyms. We also clarify when they are synonyms, like the word object with the word thing, the word substance, and so on. Okay, so those are just clarifications. We don't need them, but we just clarify that. And we can now use these words consistently, rationally, scientifically in physics. Okay, so these are, again, comprehensive definitions. So you see where we're coming from with all these definitions. So that if people have questions, well, you can always come back to this presentation, this lecture, and find out why we have different ideas than all other people out there, because no one has done this ever. They haven't gone through the words, and a lot of people, again, like the etherists, they believe, you're just doing word salad, Bill, this is just noise. Yeah, it is for noise when people are, dense between the ears, or maybe have nothing between them, no shape. Okay, so here's the next word we need to define, distance. By the way, these words have to be defined in a certain order. You cannot define a concept before you define an object, as you will find in a second. Okay, so it's got to be done in a certain order. Maybe a couple of them can be switched around, but not all of them. The word object is the number one. You can't, you need that as number one. Actually, there's a previous one, which is the word definition itself. So we need to define what a definition is. I haven't done that. here. It doesn't really belong to physics, it belongs to science. Okay, that's why it's not there. But anyway, distance, separation between two objects. Distance is simply, the space, the nothingness that we just defined between two objects. That's all it is. Okay, and the mathematicians they all confuse it with with length and with distance traveled. Actually, in mathematics they measure everything, and so it's a problem because since they measure when they talk about distance, they're really talking about the tip of the measuring tape. They're unrolling the measuring tape, or they create a tile. They say that's a meter, and now they count meters with a clock. They say, oh, there's been 10 seconds, one tile per second, so we have 10 meters. So they're always talking about distance traveled, not distance or length. Okay, for them, distance and length, in fact, are synonyms, and distance traveled, because what they do is unroll the tip of the measuring tape. They're interested in numbers followed by units. They're not interested in qualitative stuff like separation. And that's a problem. That's got, the measurement stuff has nothing to do with physics. In physics, we're interested in separation, qualitative stuff. Yeah, I know you have it. Okay, so it's unrolling with a measuring tape. And then the next word we need to define, and this one needs to be defined in a certain order after distance, right? And that's the word location. You need to know what location is in physics. Qualitative location, not the position of mathematical physics, which is a pair of numbers of how to get somewhere. In mathematical physics, position is motion. That's the irony of that, because they have this ordered pair or maybe triplet or whatever, and they need two numbers, and what they're telling you is, look, if you go 10 meters to the right and 5 to the north or whatever, you'll find a treasure chest. So that's the position of the treasure chest. That's not what it is in physics. We're not giving you instructions on how to get there. We're saying, look, distance is separation, and then the separation of one object with respect to all others in the universe, right, the set of distances, that's going to be location. That's a location of the object in the system that you're, considering. Okay. So, we like to say that location is not the same thing as position here. Okay, so in physics, we have location. In math, they have position. They're not synonyms in physics. Position in physics, we don't have use for the word because position is the object itself. It's the volume occupied by the object. And so, it's an irrelevant word. That's why we don't use it. Okay. Okay, so let's move on here. The other famous word in physics is the word exist. Physics is the science of existence. We need to define the word exist. No one has done so in the last 10,000 years. That's why we have atheists, agnostics, and theists running around in circles. Does God exist? Well, I believe God exists, and I don't believe God in God existence. And they go around in circles constantly, and no one has ever defined the word exist, so not a single one of them knows what they're talking about. That's why we need to define these words. And the word exist belongs exclusively to physics. It doesn't belong to metaphysics, ontology, or philosophy, or all the other nonsense created by the Greeks and rubber stamped by the 17th centuries. Okay? No, exists, physical presence. It's an object that has location. That's why we had to define distance first, then location next. Finally exist, right? And here are some synonyms that they use that you'll find in the dictionary. And again, people say, well, it's the actuality, it's real, reality. No. Those are synonyms. You can't use those words to define the word exist. Okay? But all you'll find in the dictionary is synonyms, and people just use synonyms thinking that they know what existence means. They don't. Nobody has ever defined the word exist. You can go and see people like David Hume or Immanuel Kant, or even modern day Ayn Rand. None of them ever defined the word object, the word entity, the word thing, or the word exist. You won't find a definition. They went around in circles, and to this day we don't have a definition from any of those so-called philosophers. Okay, and the final word that we're going to define, well, the next to the final word, next to the last, motion, two locations of an object, okay? So you can define motion before it exists, no problem, but you can't define it before you define the word location or distance. You need distance and location to define motion. You need to understand distance and location before you can understand what motion is. And again, it's two or more locations of an object. You will note that we haven't defined time. We don't use the word time in physics, okay? In the religion of mathematical physics, they use it. In physics, we don't. We have no use for the word time. We're not going to explain anything with time, okay? We don't need that word at all. So people say, well, yeah, you know, we don't need it. That's why we're erasing the whole board, starting all over. Again, we're only defining the words that we absolutely need to define. And the last word is the word concept, okay? Here it is, okay? A word that invokes or embodies two objects. What does that mean? It means first you need to define the word object before you can define the word concept. And what is a concept? Essentially a relation. Okay? You're contrasting two things. That's what concept is. It's a word that invokes or embodies two objects. All concepts embody or have inside that word, whatever concept you can think of, it's got two objects implicitly in there. Okay? And what a concept is essentially is a relation performed by another object known as a human being. Okay, so those are the foundations of physics. Take it or leave it. You don't like my definitions, you think they're BS, no problem. That's what we're here for. You don't like them, challenge them and provide something to replace them. You can't say, well, I don't like your definitions. Yeah, because they destroy your religion. That's why you don't like them. So if you don't like the definitions that you've just seen, no problem. Criticize them, show what's wrong, what's irrational. Not wrong. Wrong means that you just don't like them. Right or wrong means opinion, you know, and we don't do opinion in science, that's religion. Now you have to show what's irrational about them. For that you need to define the word irrational first, like we did. And then you have to provide your version of a rational definition in exchange for what I put up there. Okay, so now you know what you got to do if you want to do homework. Okay. Okay, let's move on to the main course today, and that's going to be the entanglement. What is entanglement? And a lot of it has to do with what we just covered. You know, that's why that long introduction. Entanglement, essentially, this particle affects that one, quantum particle, right? Something you can't see. This particle affects that one over there with nothing in between. So this one somehow moves that one or forces it to do something, and there's nothing in between. And, you know, people say, well, Bill, you don't know nothing. What do you know about this? Okay, no problem. Today we're going to let the horses talk for themselves. They're going to come out of the horse's mouth, okay? And here we have one gentleman. He's going to tell us a little bit of what entanglement is. His name is Brian Greene. I'm sure a lot of you know him or heard of him. Otherwise, you probably, it's the first time in physics for you, or mathematical physics. So listen to him. Okay, here he goes.
Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected.
So what is good old Brian, Mr. Greene there saying? Well, he's saying that no matter how far away the particles are, they still influence each other physically. And according to him, right, he says there's no mediator. Even though they illustrate a mediator, that greeny thingy that you saw there, they put that in there by hand, but then they tell you, by the way, you know, it's not there. So the greeny stuff there, that squiggly thing, was just to show you that one influences the other, but they claim, the argument is that that greeny stuff does not exist. There's nothing, absolutely nothing between the two particles. Okay, that's the issue. Okay, and so we have here another gentleman. His name is Neil Tyson or Mike Tyson, something like that. I think he's a boxer. Neil Tyson, what does he say? He says that particles talk to each other. Whoa, they talk to each other, blah, blah, blah. And I can talk to you, and I don't need to have, I do need to have a mediator. I need to have air, because without air I can't talk to you. So I do need a mediator. But again, he says that there is no mediator, but then he says something so strange. He says that everybody in mathematical physics understands entanglement. They understand entanglement? I mean, listen to him again. Don't listen to me. Here he goes.
What happens in quantum physics is that particles can know about each other instantaneously at a distance. So entangled particles communicate with one another faster than the speed of light. It's very well understood.
Okay, so we have someone at least that understands, this thing he called entanglement, this phenomenon. Turns out we have another gentleman. His name is Alex Filippenko. Let's hear it from the horse's mouth again. And he says the opposite is no one understands entanglement. And just listen to him.
It may suggest that information has traveled instantaneously. Information has traveled instantaneously. Information has traveled. Information has traveled faster than the speed of light from one particle to another. I don't understand it. I don't know that anyone does.
Oh, poor old Alex. Yeah, these people, they just swallow stuff at the university and they just repeat what they heard. That's all they do. They don't have a capacity to even challenge what their professors are saying. And that's a big problem. And so, but there's a big problem in what Alex just said. He says that he's talking about particles. What are particles? Here you have another fellow. His name is Sean Carroll. And he says there are no particles in quantum mechanics, in all of quantum mechanics. Listen to him.
In quantum mechanics, you're fundamentally not a set of particles. You're a set of waves.
So remember, you're not a set of particles. You're not made of atoms, or all that is just wavy stuff, whatever those waves are. But it's all waves. And so you got to look at the word wave. I mean, what are they talking? What is Sean talking about? Well, he's saying, a wave is made out of fields, right? And okay, what is a field? Well, it's a value at each point in space. And what is a field made out of? Well, you see those arrows there. Those are vectors. And what is a vector? It's a magnitude and direction. So all we're talking about is numbers. Value is a number. Magnitude is a number. And they have all these numbers, and they're moving to the right. Very scary stuff. They say, look, we have all these arrows that represent numbers, and they're moving. So we have the motion of numbers. They move one way always, in one direction. So it's very scary stuff, I don't know. You have to think for yourself to see if this makes any sense, what you're staring at right there in front of you, because that's exactly how they illustrate it. They think they're moving a physical object when they're moving the word field, when they vibrate their fields, and they're not. What they're moving is magnitudes, and nobody realizes that. They say, oh, the wave is moving. No, that's not a wave. It's a wave of what? Of arrows? What are those arrows? Well, they're magnitude and direction. They're just numbers. Okay, so this is one of the problems we have. And so the question, that the first question pops up, is quantum about waves, or is quantum about particles? Or, what are they talking about? What are these particles? What are these waves? And fortunately here we have a fellow, his name is Lenny Susskind. He's a guru, a string guru. Apparently he studied a little bit of quantum mechanics, so he's going to tell us exactly, whether quantum deals with particles or with waves or with both or what. Here it goes.
Particles are particles, waves are waves. How can a particle be a wave? A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles.
And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
So did anybody ever in the last 100 years of quantum mechanics ever decide to challenge the nonsense that all these mathematicians are presenting? They're saying that we have waves and we have particles, and someone is telling you, and that's what Lenny said here, that a particle is a wave and a wave is a particle. Well, that makes no sense. Like he said, don't take my word for it, but he's telling you in your face. And nobody challenged that and saying, hold it, how are we talking about waves or are we talking about particles? And they're talking about both, essentially. They're saying that this thingy called the quantum has both things inside it. And so depending on the experiment, well, it'll show the aspects of a particle or the aspects of a wave, even though a wave is also made of particles. So exactly what they're talking about, are we saying that it all reduces to particles anyways, whether it's wave or particle, because all waves are made of particles? Or are waves made of, what was it, vectors, fields and vectors, numbers, values, quantities, magnitudes? Okay, but here we have good old Sean Carroll again. He's going to tell us something else. He says that even the waves that are made out of fields, even the fields get entangled. So now we have something interesting here, because now we're not only talking about particles getting entangled. He's saying the particles themselves are vibrating fields, locally vibrating fields, and the fields themselves get entangled. They affect one another at a distance. So listen to him. Here goes.
What do quantum fields in a vacuum look like? Empty space.
Just so, like empty space. It's as empty as it can be.
But there's still a field. It's just,
yeah.
What is nothing?
We now know that, the reality of our best way of understanding the world is through quantum fields, not through particles. So even the electron, not just gravity and electromagnetism, but even the electron and the quarks and so forth are really vibrations in quantum fields. So even empty space is full of vibrating quantum fields. And those quantum fields in empty space are entangled with each other. This location in space, there's a gravitational field, which I can detect by dropping something,
yes.
Right? I don't see it, but there it is.
Okay, so now you see it. What's happening here is that these people are using this wave and particle duality to get away with murder. You challenge the particle and they say, no, but it's a wave. Oh, okay, and how about the wave? No, it's a particle. And what is a particle? It's a vibration of a field. And what is a wave? It's made out of fields, and the fields are made out of vectors. And so you never learn anything because it's all just math. And in other words, you never learn anything about physics. That's what I meant to say. Okay, we don't have any physical interpretations for entanglement. Why? Because all these people are moving concepts around. They're talking about concepts. They're reifying these concepts, concretizing them, turning them into concrete, reified objects, and then they start moving this concept around, which they treat as a physical object. That's where the problem is. And so because of that, they don't understand squat. And here you have another gentleman. He's from MIT. His name is Walter Lewin. And he's going to tell you, what he knows, exactly what he knows about entanglement. Here it is.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement. It is impossible to even comprehend. Don't even ask me why. Don't ask me how it works, because it's an illegal question.
Okay, so don't ask. Please don't ask, because we have no answers. Yeah, they don't have any answers, and but that's what the kind of questions people ask. I mean, the common man out there, he wants to know, why this spoon falls to the floor. He wants to know, oh, the entanglement, this particle affects that one over there. Well, how does it do it? I mean, well, there's nothing in between. Yeah, so how does it do it? Well, let me tell you about fields and about waves and vectors. We're not going to have a physical interpretation for what's happening there. And so they don't have any physical interpretations, or like Mr. Richard Feynman says, they've given up on that. But those are the kind of questions people ask. People want to understand how this universe works, and we've got the wrong people giving the answers, or supposedly doing the research to try to get you an answer. They themselves, on the one hand, do the research to try to figure out how this universe works, but then they tell you, well, it's not our job. So whose job is it? Who's going to tell you how this universe works? Is it supposed to be a biologist, a paleontologist, a historian? I mean, I don't know. You tell me. I thought it was the job of a physicist to tell you how this universe works. And they've given up on that, and we're expecting them to give you an answer, so you're going to have a long wait, believe me. And here's one of the reasons they can't answer. This is Sean Carroll on the uncertainty principle. What is the uncertainty principle? Well, it's that you cannot know the position and at the same time the motion of a particle. You have these two things. That one is a static concept, the other one is a dynamic concept, and they say, well, the more you know about the position, the less you know about momentum, and the more you know about momentum, the less you know about position. Yeah, no kidding. One is a static concept, the other one is a dynamic concept. And it's got to do with this notion of particle and wave. The wave stretches out and vibrates, whereas the particle, you can say, well, at some point, it's got a location. So now I put my detector, whatever detector you use, and you detect the location, the position of the particle. Well, at that point, you don't have a wave because the wave is stretched out and always vibrating. The more you know about the wave, meaning, the momentum, the motion, whatever, the less you know about the location, the position of the particle. And so here it is. Listen to him. Again, he's going to tell you in his own words. Give me a second here. Here he goes.
We wouldn't be able to know exactly that you had a position and velocity at the same time, right?
Mm-hmm.
The old joke about Werner Heisenberg being pulled over and the cop says, "Do you know how fast you were going?" And Heisenberg says, "No, but I know exactly where I am." Because you can't know, according to the Heisenberg uncertainty principle, both your velocity and position at the same time.
Rocks it.
If I were a cop, I would give him a ticket. Put them in prison, Yeah, so all these people, the big problem with them is that they're reifying concepts, mathematical concepts. That's why they don't understand. And if you have all these supposedly, these supposed principles like the uncertainty or indeterminacy principle, they create all these nonsensical principles based on the notion of the particle and the wave. It never occurred to them to get rid of both of them, wipe the board clean, and start all over again. Here we say that what they've been looking at all these years is a rope. Rope is a physical object, a pair of twined threads. That's what a rope is. That's the mediator of light, and it's the mediator of gravity. Now you have a physical entity, you can at least give a physical interpretation and, show them what you've got, what your theory is about. But these people can't do that. Because what are they going to put on the board? Energy? Is that what they're going to, how do you illustrate energy? What are they going to put, a wave? What is a wave? Well, wave is fields. What is a field? A field is a bunch of vectors. So all they're having is numbers. They can't put any of those, they can't illustrate any of those on the board to give you a physical interpretation of any phenomenon, especially invisible, intangible phenomena out there. That's where the problem is. So yeah, we go back to where we started early. You got to know what science is. What is the purpose of science? Rational explanations. Physics, which is what we do here, causes and mechanisms. In other words, rational explanations of causes and mechanisms. Okay, and the job of a physicist is not to be a detective, to research, to do experiments out there in his dark basement. His job is like that of a prosecutor, to explain to the jury or to the crowd or the audience his theory. The only way he can explain his theory, meaning a physical interpretation, meaning a mechanism showing the causes, is by putting something on the board. And there better be some kind of drawing, some kind of image out there that he can point to. And so you can follow his presentation because you see it all on the board, right? And here, here's the fact that these people use concepts as objects. And we have the famous case of, especially lately, I've had a few ethers come over, and they propose the ether. They don't realize ether is a concept. It's not a physical object. And again, you need to know the difference between an object and a concept. There it is. Okay, you don't like the definitions because it destroys your religion? No problem. Come and criticize the definitions, okay, and put something in exchange, because I'm saying that your ether, so-called ether, is not an object, not a thing. So you got to tell me what a thing is. You don't like that definition. And yeah, some of them say there's nothing on the outside of it, so how can we know what shape this ether thingy is, and what is that thing that's on the outside? Well, they say there's nothing there. Well, yeah, every object has nothing outside of it. And nothing is what is outside of something. Okay? That gives it shape. Anyways, those are some of the words that you see there that mathematicians and other people, dissidents, treat as objects. None of them are objects. You can't use the word field, energy, mass, force, time. None of those words qualify as objects. And none of the ones used by the plasmoids, the thunder bolters, the people from the electric universe who use words such as plasma, electricity, and charges. None of those are physical objects. Okay? And people say, what do you mean electricity is not a physical object? Stick your fingers in an outlet and you'll find out if it's an object. So this is the way the electric universes prove an object. They say, stick your fingers in an object in the outlet, and you'll know. If you get a kick, then you'll know what an object is. Okay, ethers, they use the ether, and you have flat earthers. All these people, by the way, they use the same ones as the mainstreamers that they criticize, but they also have these other ones which are their pet peeves, such as density and pressure and so on. So yeah, this is the problem. The problem is language, and until we correct the language, until we understand what physics is attempting to do, what science first and what physics second is attempting to do, if you think that physics is about giving physical interpretation, giving you the causes so that we understand how this universe works, then you need to go through the foundations of physics, which includes all the words that you must define before you do physics. And no one can skip them. And you can't go to the dictionary and say, well, look it up in the dictionary. All the words that we just saw in the dictionary are irrational. They have not one of them has a valid definition that can be used in physics. And so, yeah, never use the dictionary, never use an encyclopedia, because they were written by people who are not physicists, who are the ones who have a stake in those definitions. And with that, I guess I'll see you next week.